The chain rule, for when you do one thing and then right after do another thing. That's called function composition. Chain rules for the special case that the function you're chaining into only takes one input. Set up the situation. Start with x. It goes through some function giving you a number g. That number gets put into a function which only accepts one input, f, and gives out the number f. So g is a function of x. F is a function of g, which is a function of x. Let's look at a specific example to illustrate. X goes through the exponential function, giving you e to the x. That goes through the sine function, sine e to the x. So e to the x is like g of x, which is a number, g. Sine of e to the x is f of g of x, which is f of g. Let's put all this into the calculus schematic to make sense of it. Our second function, g goes through the f function, giving me an f value, f of g. So that g-axis is the same for both graphs. Get our derivatives, get our tangent lines, and put in our differentials. Slope, g prime of x, rise over run. Same g-axis, same dg differential. Slope, f prime of g, rise over run. So the composite function outputs f, inputs x, and so I just put those two number lines against each other. There's my composite function. There's my chain. Put in my differentials. That dictates a slope. I don't know what f prime is because I don't have that function. I don't have f as a function of x, so I don't know what the slope is. Rise over run, that slope. But df dx is just df dg times dg dx, canceling the dg's. df dx, the derivative of f of g of x, df dg, f prime g, g prime x. And so there's the chain rule as written in the book. Let's do an example just to see how the pieces fit together a little more carefully. So we have our exponential function. That's going to be mapped onto the g-axis. We have our sine function, which takes g as an input and maps it on the f-axis. We have our derivatives, because these are elementary functions. So I know g prime. I know the derivative of sine, that's elementary function. So I know f prime. Remember, f prime is just the slope number. F is just a number on the f number line. G is a number on the g number line. G prime is just your slope number. So for our differentials, and dg does the handoff. I can replace dg by g prime dx. Put it in the schematic real quick. X is our input, e to the x is our output. And our slope we know, it's e to the x. Set up our differentials. dg is the slope e to the x dx. Set up the schematic for f. It's for the sine function. My input is e to the x. So sine e to the x is my output. I know the slope is cosine. Cosine at the point, so it's cosine of e to the x. So my differential, df, cosine e to the x dg. Replace dg by what it is in the other drawing. df is cosine e to the x times e to the x dx. But this differential statement comes from a function whose input is x and output is f. It's the composite function. X goes in, sine e to the x comes out. So that's our f function, the composite function. Its differential satisfies df is f prime dx, where f prime is the slope on the fx plane, the graph of f. Chain rule says multiply the derivatives in the map. Set up the calculus schematic for this function. X is the input, f is the output. So there's our graph of f as a function of x. Its slope is f prime from the differentials. Cosine e to the x, e to the x. F is a function of x, and so this is f prime of x. More precisely, it's the derivative of sine e to the x. Notice in the map of the composite function, multiplying each piece is the derivative of the composite function. That's the chain rule. Here's the takeaway for just computing later on. When you map out your function and you see this connection through one number, that's a chain, and you're going to use the chain rule. So when you take your derivative, you write down your derivatives of the elementary functions, and then you multiply the derivatives together. That's the chain rule. Chain your functions, and you multiply your derivatives.